Good morning, peoples. This is one of the Maths Learning Centre's revision seminars. Today we're going to be talking about stuff from the Maths for Information Technology course. I'm just going to work out how to make this. I asked you to go to the document camera half a dozen times. So we're going to talk about modular arithmetic to start off with, and I'm going to work out what I did with all my pencils. Pencil sharpener. Awesome. So someone left something here for me to sharpen pencils into. Okay, so what do we know about modular arithmetic? The idea is that with a lot of these things, what we're going to do is we're going to try and compare it to what we already know. All right. So we know about ordinary arithmetic, and so. Wondering. I'm a man, so I can't talk and write at the same time. One of those things. My wife claims I can talk in my sleep, but okay, so we're just going to go with, and I'm going to work out where I wrote it down, a couple of basic things, all right? And I'm sure I wrote it down somewhere. So I did actually spend a moment looking at your lecture notes. I got really bored, and so I thought, oh well, I'll come here and I'll wing it. So if A is congruent to X mod N and B is congruent to Y mod N, if I want to do something simple like just add them up, alright, if I do A plus B, what can I say about it? Well, that's going to tell me that it's congruent to not A. So this is what I mean. Give me a moment to warm up. X plus Y mod N. So if I'm adding two numbers that we know are modular and congruent to something or other, then we're basically adding those values that they're congruent to. Possibly what we should say is this means that A minus X is, so A minus X is divisible by M. Is that the way, N? Is that the way you've been writing it in lectures? This means this thing is divisible by N? No? Never seen that before? You have? No? Okay, awesome. So that is a K such that, you know, we'll see me do S dot T, which will be such that, because it will happen eventually, A minus X is equal to some K by N. Alright, so we're going to say that K is in the integers. So basically, when we're talking about congruence, we mean the remainder. We understand after doing all our discussion about equivalence relations that the congruence is an equivalence, giving me an equivalence class. And so when I say A is congruent to X, A and X are any members from the same equivalence class. Usually the point about doing congruence though is we want to represent it with a smaller number. All right, this is one of those things, whenever we're doing this sort of arithmetic, we're going to choose the smallest number because that's what makes it easier. All right, and we have the option of doing what they refer to as least absolute, so positive or negative but smaller, or least positive. Most number theorists will actually go with the least positive, but that's a preference thing. Okay, so depending on the situation you're dealing with will determine what you're trying to do. Okay, so the next thing on the list would be that A times by B is congruent to X times Y mod L. By the same reasoning, we're going to come up with that sort of idea. Now, so we're all good with that? Yes? I was going to say yes. That's easy stuff. So, I'm not going to go into some of the other things that I've seen around in terms of congruence properties. What I'm thinking is the difficulty with this sort of stuff isn't so much the actual arithmetic. It's things like finding the inverse of an element. Yeah? And finding the greatest common divisor, following like the Euclidean algorithm. Because I looked at your lecture notes and I thought, why is there a matrix thing in there under the Euclidean algorithm? And I'm going, when I actually worked out what they were doing, okay, that's kind of clever. They've done some of this calculation, they've said, we can express it as a matrix multiplication, which means we don't really have to understand exactly what's going on underneath it. Okay? And we can do that. So sometimes when we're doing this sort of thing, we can either understand exactly what's happening, or we can know a process which will allow us to calculate the thing we want. So what I'm going to do is I am going to talk about the Euclidean algorithm for a second. That's it. So if I've got two numbers, let's go, what did I use? I used A and N. Heavens knows why, but we did. So greatest common divisor, let's go A and B. Now, I'm going to pretend this number is G for the moment. Now what we're saying with this sort of thing is that my G divides both A and B in this case. Okay? So that means that if I divide out that factor, there'll be nothing left over, effectively. But we should be able to do this thing. So if I write A, I'm going to assume A is equal to, so we're going to go Q1 by B plus our remainder 1. Okay? So my quotient here, nothing to do with it. Just the largest number so that I can take off some amount. A can be expressed as some multiple of B plus R. Now, if A is divisible by this G and B is divisible by G, then this R has to be divisible by G. G divides A and G divides B, then G divides R1. You know, I might have done that. Yeah, I'm going to go, I'm going to go, which way around did I actually write it? Check. Yeah, so we're going to go back up here, and this should be the other way around. M divides A minus B, A minus X. Alright, my apologies for that. Some of these things, they tell me that a good portion of mathematicians are actually slightly dyslexic. And so get the notation around the right way. So my key point is G is going to divide that remainder. So if I repeat this process, right? If I shuffle things along, if I move my B over, B is equal to some Q2, and I put my R1 here, then my R2, then G should also divide my R2. So you see how what we're doing is we're creating a little bit of a chain where that thing is always, in theory, this is reducing, all right? We're always, because we're trying to make this sequence, sort of A, B, and then R1, R2, R3, whatever, decreasing sequence. And it will have an endpoint. All right? Ultimately, we will get to a point where we're going to divide out. All right? There's going to be no remainder left over. Every time we're reducing the number, at the end, we'll have no remainder. So we're actually making sure that A is greater than B, which is greater than R1, which is greater than R2. And so we're going to have an endpoint. So if we keep doing this, so I'm just going to put in, we're going to have R1 is equal to Q3, R2 plus R3. And so ultimately we're going to have an Ri minus 2 equal to Qi Ri minus 1 plus, now I wanted to go, that's what I wanted to do. I wanted to do that. Ultimately, we're going to have plus 0 here. Okay, so ultimately we're going to stop. And that's the key point here. We're going to stop. So whenever we do an algorithm, we want our algorithm to stop. All right, if you do much computer science, and maybe that's why you're doing this course right now, you want to know that your program's going to finish. All right? So you'll talk more about how you're going to, when it's going to finish, but moreover, you want it to finish. And so this means that Ri here has got to be equal to G, the greatest common divisor. Okay, so this process has actually gone through and found this thing. Okay, so what we're going to do is we're going to digress for a second. Do I need to leave that up there for a second? So what we're going to do is we're going to try an example. No. Okay. We're good? The other thing to say about this is with all of our seminars, what we're going to do is we scan the information here and we post it online along with the recording. So sometime later this afternoon, or possibly first thing tomorrow morning, all these material will turn up online, and you will see the video links and the material I've written out. So where did my numbers go? Did a fancy example just to work out what's going to happen. All right, so we want the greatest common divisor of 329 and 126. If you're looking in textbooks, sometimes, particularly number theory textbooks, they'll just abbreviate that to just brackets, like a tuple. Now, we're always going to start with the largest number, okay? So we're going to have 329 is equal to 2 by 126 plus 77. Okay? So I've deliberately chosen numbers that hopefully you can't just see what the answer is off the top of your head. Unfortunately, there's going to be a few steps. But what we're going to do, we're going to build this up. We've got A is equal to 329, B is equal to 126, Q1 is equal to 2, and R1 is equal to 77. All right, always good to sort of place yourself, know where you're going. All right, so my next step, move everything over. So my 126 goes here, there's going to be 1 times 77 plus, and we're going to assume that my working out prior to this is correct, and go, sweet. And so now what I've got my Q2 is equal to 1, and my R2 is equal to 49. At this point in time, we might have a bit of a guess what the greatest common divisor is, but we're going to move on and see if there's not something else we can find out. So, move my numbers over. My 77 is equal to 1 times 49 plus 28. So again, Q3 is equal to 1, R3 is equal to 28. Move numbers over, so 49 is equal to 1 times 28 plus 21. Q4 is equal to 1 and R4 is equal to 21. So this bit on the side here, this bit on the right here, you don't actually need to do, but sometimes it helps depending on what you're asked to do. And for the purposes of what I'm trying to do here, I'm trying to keep a track of what we're saying, going from what we've said in the algorithm. So what we've said the algorithm is, just pause momentarily, so we've got this in terms of Q1s and R1s and QIs and RIs. So we're trying to make sure that we're putting that information here as well, so that we know where we're up to. We know what we're doing. So move things along. Now, I am going to move fairly fast through this. Plus 7. So Q5 is equal to 1, and R5 is equal to 7. And so 21 is equal to 3 times 7. So my Q6 is equal to 3. There is my R6 is equal to 0. That means I've stopped. So that means that the 7 is my greatest common divisor. So we're all good with that? Yes.
How did you obtain Q2 and R1?
Q2 and R1. How did I? So right at the very start here, when I'm. So the very first step, I sort of said, if I time 329, if I look at the 126, so my brain just did the 2 times 126 is going to be 252. The difference between sort of that and the 329 is less than 100, and so definitely less than 126. So that's the largest multiple. So I'm actually trying to make sure all of my remainders are positive. In actual fact, I could do it with negative remainders. All right. So if you look at the second one, my 126 is equal to 177. I could have actually written that as 2 by 77 and then minus whatever the appropriate amount is, and that might have made the whole process shorter. One of the reasons we're doing it this way, all right, is the next step of this, the bit that this whole matrix stuff that you talked about in lectures is about expressing that greatest common divisor as a linear combination of those two numbers to start off with, okay? And so they've developed this fancy little thing. So normally what we did when I went through is we actually backtracked along this algorithm. All right, we sort of said that. So we sort of started here and go, well, 7 is equal to 28 minus 21, and so is that the right way around? Yes, and so what we can do is we can rearrange this and say 21 is equal to something in terms of 49 and 28. All right? So, what the hell? Let's see if we can do it here. So, from here, we can see that 7 is equal to 28 minus 21. But because I can rearrange this one here, I can say 21 is equal to 49 minus 28. So as this is equal to 28 minus, and then 49 minus 28, which with a bit of simplification can become 2 by 28 minus 49. We're okay with that so far. Yep. My next line here, we go up a bit, we've actually said that 28 can be 77 minus 49. So let's go 7 is equal to 2 by, so 28 is 77 minus 49 minus 49. And so when I simplify this out, this is 2 by 77 minus 249, so minus 3 lots of 49. Let's put a multiply in there so it looks like we're actually multiplying those things together. So, just there we go. Now, so my 49 is 129 minus 77. So 7 is equal to 2 times 77 minus 3 by 126 minus 77. So again, we're going to simplify this out. And so I'm going to end up with, so I've got 2 by 77 plus 3 by 77, so that's going to be 5 by 77 minus 3, 5 times 77, minus 3 by 126. 77 the very last one that I can do this for is equal to 329 minus 2 lots of 126. So this is going to be equal to 5 by 329 minus 2 by 126. Whoops, sorry. Let's give ourselves a little bit more room here. And then minus 3 times 1 times 126. So if I expand this out, I get 5 times 329. This is going to get me 10, so minus 13. Is that right? Let's pretend. Alright. This number here is about 1600. This number here, very close to 1600. That's probably right. Okay? So I've expressed 17 as, this is like sort of S by A, S times A plus T by B. Alright? And so I can write it as a linear combination of those things. And so in actual fact, this is just one combination. Alright? This is just one that works. Alright? Now we know, so S is equal to 5 and T is equal to minus 13. So I'm going to whack in a naught to indicate that that's a particular solution. Alright? With anything we're going, how many solutions can I possibly have? And the idea is, if I go, if I add the right amount of this thing and the right amount of that thing, then they're sort of going to cancel each other out. Yep. So if I divided this one by 29, I'd end up with 47. Yep. Otherwise I can say yes, I reckon. So if I did 47 times this, and I did 18 times this, then I'd end up with the same number. Alright? So if I have S is equal to 5, alright, so S is timesing the larger number, so we're going to times plus, so if I do 18 times some integer k, alright, some integer k, and I do T is equal to minus 13 minus 47 times k. When you expand this out, when we do S by 3, S times 329 plus T by 126, what's going to happen? 329 times this is going to get me a multiple of a 126, and that will be the same multiple I get when I do 47 by the 47 times the 126. And so they will cancel each other out. Okay? Maybe we should write it out to see what proves my point. So 5 plus 18k by 329 plus 126 by minus 13 minus 47k. Ooh. So I've got my 5 times by 329, and I've got my minus 13 by 126. We know that bit's equal to 7. When I do plus 18 times by 329 minus 47 times by 126. Okay, this bit here should work out to be 0. Really love a calculator to be able to work that out. Did it work out? Awesome. I love it when a plan comes together. Yes?
To get those numbers, do you just divide your A and B by 7?
Yep. So this divided by 7, 47. The 126 divided by 7 turns out to be 18. All right. 140 take 14. Nice and easy. Cup of tea. Okay, now, that's awesome. That's how we used to do it. Okay? So, what I'm going to do is I'm going to put this over here. Now, I'm going to put now 3 up the top of this page, and we're going to do MIT. Alright. So, your lecturer told me something really clever. It was like A naught is equal to the identity, 1, 0, 0, 1. Qi is equal to 0, 1, 1 minus Qi. Minus Qi, awesome. And AI is equal to Q. What did he say? Where did I write that bit? I've written it somewhere very carefully. I probably put it. Ah, there it is. Q I A I minus 1. Okay. So I thought to myself, I actually thought, why on earth do I want to know that? Is what I actually thought. But this process here is that matrix method where we can actually go do the same thing. All right? So what we're saying here is, I'm going to just write them out. So Q1 is equal to 0, 1, 1 minus 2. Q2 is equal to 0, 1, 1 minus 1. Q3 is equal to 0, 1, 1 minus 1. Q4 is equal to 0, 1, 1 minus 1. Q5 is equal to 0, 1, 1 minus 1. There is no Q6 because my remainder is 0, so we stopped. So if I do this, okay, if I go ahead and do this, it will be a long, tedious calculation which I will jump at some point in time. I will give up on. So, but I'm going to go A1 is equal to, so Q1, 0, 1, 1 minus 2. Times by, so Q1, A naught, 1, 0, 0, 1. Nice and easy because it's the identity, 0, 1, 1 minus 2. A2 is equal to Q2, 0, 1, 1 minus 1, and then 0, 1, 1 minus 2. Okay, so 0, 1, and then 0 minus 2. In actual fact, this process is, the structure of this matrix is going to take the bottom line, the bottom row of the second matrix and make it the first row, and then we're going to do a little bit of combination of things. So we're going to go 0, so that's going to get me minus 1, 1 plus 2 is going to get me 3. Sweet. A3 is equal to, so Q3, 0, 1, 1 minus 1. This is where I wished I'd chosen an example that didn't have quite so many steps. Bottom line becomes the top line, minus 1, 3, and then 1 plus 1 is going to be 2, and 2, so minus 2 minus 3 is going to get me minus 5. And so my A4 is going to be equal to Q4, oops, Q4, 0, 1, 1 minus 1, and then A3, minus 1, 3, 2, minus 5. Okay, so 2 minus 5, minus 1, minus 2 is going to get me minus 3. 3 plus 5 is going to get me 8. A5. Yeah. 0, 1, 1 minus 1. And then 2 minus 5 minus 3, 8 is equal to, so minus 3, 8. And so we're going to get 2 plus 3 is going to be 5, minus 5 minus 8 is going to be minus 13. And this here is my S0, and this here is my T0. Let's push that a little bit so we see that at the bottom there. So this process has given me the same answer as what I had by doing it the old-fashioned way. All right. Arguable about whether it's which one is easier, but it's doing the same thing. It's actually taking out some of the understanding of what's going on and just going, it's a process I can follow. All right. And sometimes, if we're not sure what we're doing, process I can follow. So you can go either way. Are we all good with that? Nod wisely and say yes. Awesome. Okay. So that was sort of, that's the having a scan over the things you've been asked. That was sort of the first thing that sprung to mind about what's causing us difficulties. Okay. Oh, do you want that up? Do we need that? All good? So the next thing is actually using modular arithmetic in terms of calculating sort of ciphers stuff. Okay? And the key thing about that is actually calculating the inverse. Yes? So we need to understand we need to actually be able to find our greatest common divisor, because one of the questions we're going to ask with our ciphers is, are the numbers involved relatively prime to each other? If the answer to that is yes, then we can be fairly confident that we're on the right track. All right. So, I'm going to digress a little bit. You find I do that a lot. Just as far as I see, there's like ciphers and Chinese remainder theorem. So, don't leave that. If you looked over my working, you would have seen lots and lots of pages where I've gone, what the hell is going wrong with that? Because amusingly enough, the first thing I do with the Euclidean Algorithm is get it wrong. All right, so we're going to put 4 up the top of the page. That's IT. So I'm just going to add in a couple of things. All right, so when we're talking about the integers mod n, if n is not a prime, then we can have my congruence classes come down to either being what we'd refer to as units or zero divisors. That is, unit. So, okay. So, your lecture notes literally say a unit is an element that has an inverse. What does that mean? So that it means x is a unit, then we're used to the back to front e thing for there exists a y such that, again, shorthand, no mathematician can be bothered writing stuff out longhand more than a couple of times in a day. So such that x times y is congruent to 1 mod n. Is a unit. Possibly we should have in here. That's a bit of a qualifier. So if you think about all real numbers, so we actually exclude 0. Or 0 is a special case, all right? Kind of special case bucket. If you imagine real numbers, then every real number that is not 0 has a number 1 on. So if I have a real number a, there is a number 1 on a, such that a times 1 on a is equal to 1. And so the real numbers are one of these things where everything is a unit except for 0. All right? So we're trying to, with a lot of this stuff, we're trying to go how closely to the real numbers does it actually match, okay? And so this is one of those things we're going, hey, sweet, it does that. Now, when we start, so if I did just mod, if my modulus was a prime, if my n happened to be some prime number, then everything except 0 would be a unit. All right? But the other class of things, the zero divisors. So my zero divisor is a number, if I times it by something, will give me 0. So if there is a something, so for my x, if there is a y, that gives me 0, it's a zero divisor. Zero divisors not making our life fun, okay? So it's a bit like speed bumps. They're not making our life fun, but they can make it interesting if you don't notice them in time. Sweet. So, where do I want to go? No, don't care about that. So, when we're doing our cipher type stuff, we need to know whether my element is a unit or a zero divisor. Alright? Because if it's a unit, I can find the inverse, and that usually means it's a good thing. If it's a zero divisor, basically it acts like 0. So you remember your Hill cipher. If your determinant of your Hill cipher, you know when I say Hill cipher what we're talking about? The matrix one? The determinant of that, the encryption matrix, if the determinant of that turns out to be a zero divisor, it's effectively the same as the determinant being 0, and there is no inverse. I cannot calculate an inverse for that matrix, and so I can't use it to encrypt, and hence it's not going to work. So, where was I going? Possibly, so one of the things we're implying here is my units and my zero divisors are two separate groups. So every element mod n is either the 0, a unit, or a zero divisor. Okay. So, what I was thinking, should we try and find the inverse of an element? So, where did I do that? I didn't. So, if I'm trying to find the inverse of an element, usually I think about, I try and go, so let's try, hang on, that's what I wanted to do. So first thing we've got to observe, so if my A and N are relatively prime, then A is a mod N. Okay? So if my A and N are relatively prime, then it's a unit mod N. How are we doing? And so by implication, if they're not relatively prime, would be a zero divisor. Or 0. I'm assuming we're not actually trying this on 0, okay? So if I try to find alright. So we want to try and find 7 times by some y congruent to 1 mod n mod. So first thing we're doing whenever we try and do something, say what it means. So we've gone back up, the definition said that for it to be a unit, there has to be a y such that x times y is equal to 1. If we're doing 7 and 26, let's put the numbers in. Alright, that's what we're trying to find. Now, this is in general hard to do. We can only actually do this because we have a relatively small n that we're working with. Okay? There are other techniques, I believe, that will allow us to do that, but for the most part, we just need to know it's difficult. Now, if you ask me to do this, all right, what I'm going to do is I'm going to write all the numbers which are congruent to 1 mod 26. So I'm going to have 7 times y could be equal to 27 or 53 or what was that? If I'm adding 26, that's going to be a 9, so 79. If I add 26 again, that's going to be 105. 26 again, 1, 3, 1, 5, 7, and possibly gone too far, but that's okay. 3. Okay. So I want 7 times y to be equal to one of these numbers. So I want it to divide evenly. So if I do this, 27 divide 7, it's going to get me remainder is equal to 6. Here, my remainder would be equal to 4. Here, my remainder would be equal to 2. Here, my remainder, it turns out to be equal to 0. This is if without doing the reduction mod 26, this would be the value that I can pick. All right, so 7 times y is equal to 105. Therefore, y is equal to 15. We're okay with that? Seems fair. And so, when I reduce mod 26, it's going to get me 1. So, y is, whoops, damn, sorry. So, this little trick where all I've done is written out the possible values. Because there were sufficiently few of them, I could work it out. In actual fact, I know I didn't need to go past 7 of them. If there wasn't one within 7, so you see I've only actually written out 7 numbers, then I was gone too far. All right? Because I should be able to add 26 to these numbers to get the next one. So to get another version or another element of that same congruence class. So for example, because 15 is congruent to 41, mod 26, that would be another value. All right. We're not going to dwell on it too much, but in numbers mod 26 are actually represented. Congruence classes represent a value represents a whole congruence class, and so a whole set of numbers, and it kind of can get confusing. All right, moving on. So we're all good with that? Was that just a little bit too easy? No, it wasn't. Say yes. All right. Last thing on the list of things to talk about is Chinese remainder theorem. So, my Chinese remainder theorem says something. What does it say? This should be page 5. That's IT. Okay, so what we're going to do, let Q1 up to Qm be numbers in the integers, and be, I'm going to say pairwise Co-Prime. Are we okay with the phrase pairwise Co-Prime? That means any pair of those numbers relatively prime. And so the whole lot, if I choose any pair, yeah, good. Now, and I have myself a number x, which is congruent to A1 mod q1, x is congruent to a2 mod q2, and so on and so forth, up to x is congruent to am mod qm. So basically they're saying there is a unique solution modulo, so mod q, which is equal to q1 times q2 times up to qn. Alright, so the reason they call it the Chinese remainder theorem is as the story goes, the Chinese used to arrange their troops into rows of, say, 17, 19, and 23, say, and so they'd look at the remainder, and they could know exactly how many they had up to the product of those numbers. So if I had a particularly large army, I would just go through and get them to rearrange in this order multiple times, and I would be able to produce an accurate value. So 17 times 19 times 23 is about 8,000. So I add another, say, next prime, 29, and suddenly you're talking sort of 240,000 or something or other. I forget. Anyway, big number, big number. And so we can actually know exactly how many soldiers I have. My argument would be that we don't need to know that accurately down to, like, if my army is in the hundreds of thousands, I don't need to know down to the last soldier how many I have. But the Chinese wanted to. Everybody's got their little idiosyncrasies that they're into. So how do you? So the problem isn't knowing that this is true, is it? The problem is actually being able to use this in a problem to solve a problem. Yeah, I do it in a quick and efficient way. So one of the things you're going to do. So your solution. Solution would be like x naught plus k times q, because there's multiple solutions. Now, to find the solution, so each time what I'm doing is so x naught, so x is equal to x1 plus x2 times q1 plus x3 times q1 q2 plus, and so each time I'm going to multiply by an extra factor, and so what I'm going to come up with is xm, which is going to be times by q1 q2, and we're going to stop one short. Alright, we're going to stop at qm minus 1, the second to last one. Now, the reason we're going to do this is when we put this x back into these congruences here, so we're systematically going to do this for these congruences, right? We're going to actually reduce it down. So you see, if I put this back into this first one, because all of these have a factor of q1, I don't need to consider this part. Clever, clever trick, hey? And so that's going to tell me straight away what x1 is. Then I'm going to put it into this one. Now, I know what x1 is. All these other ones have a factor of q2 in it. So the only new term is going to be this x2. Yep, are we loving it? Awesome. So, hopefully this is going to be a really simple plan. If it's a simple plan, I should be able to do it nice and easy. Yeah? So I'm going to take q1 is equal to 3, q2 is equal to 5. If you want, we can choose different numbers, but I figure since this is just a demonstration, part of the trick will be to keep it simple so you can see what's happening, and you can then try your difficult numbers later on in the piece. Yeah? Okay. And so, next trick is to go and A1 is equal to 1, A2 is equal to 2, and A3 is equal to 3. So we're let x equal to x1 plus x2 times 3 plus x3 times 3 times 5. Alright, I have 3 unknowns, I have 3 equations, I'm going to be able to solve this. Yes? Not wisely yet, say yes. Awesome work. So, my first equation said that x is congruent to 1 mod 3. Whoop, damn. Let's go up to there, shall we? And so, this is going to tell me that x1 is congruent to 1 mod 3. Sweet. Don't need to think any more about it. x1 is equal to 1. Therefore, x1 is equal to 1. X is congruent to 2 mod 5. Is going to tell me that x1 plus 3x2 is congruent to 2 mod 5. This is going to take just a little bit more working out. So I've got 1 plus 3x2 is equal to 2 mod 5. And so 3x1 congruent to 1. So this is that thing where these numbers behave just like the integers, just like ordinary numbers, all right, with my congruent symbol. If I take it from both sides, I should be the same, should get the same, I maintain the values being congruent. Mod 5. Yes, it should. You gotta watch me for that sort of stuff. Some of the stuff I've done in lectures, you just like, oh, that's very embarrassing. Fortunately, people forget these things nice and quickly. It's not like I'm the Prime Minister. So, now, am I saying because it's congruent to 1 mod 5, my options are going to be 6 or 11 or 16. Fortunately, this is the one. So 3x2 is equal to 6, which is congruent to 1 mod 5. So therefore x2, whoops, is congruent to 2 mod 5. That's a bit odd, but oh well. Wasn't expecting that. Not going to let it bother me. So my last equation said that x was congruent to 3. So we've got the value from up here, 3 mod 7. So I'm putting in my details. That's going to tell me that 1 plus 3 times by 2 plus x3 times by 3 times by 5 is congruent to 7. Congruent to 3 mod 7. Okay? Yes? Awesome. Alright, horrible numbers. Amusingly enough, what I've got is 7 plus 15 times by x3 is congruent to 3 mod 7. Because this is mod 7, I can ignore this. Not doing me any favours at all. My 15 What is 15 congruent mod 7? Remember how I said if I've got A times B, and A is congruent to X mod 7, and B is congruent to Y mod 7, then A times B is equal to X times Y mod 7. I can replace what 15 is mod 7. And that's going to reduce the complexity of the calculation, isn't it? Because that's going to become 1 times x3 is congruent to 3 mod 7. And so therefore x3 is equal to, really? Really? Did we see how easy that was? We're unimpressed, I can tell, but that's okay. So ideally I'd like to finish this here, and so my x is equal to 1 plus 2 times 3 plus 3 times 5, which is going to be 1 plus 6 plus 3 times 15 is 45. Let's go with 45, shall we? 51, 52 is equal to 52, congruent to 52. So x is congruent to 52 mod 3 times 5 times 7 is 105. Sweet. Amusingly enough, that is what I said. And if we go back and check, we can see that it's going to be the right values. All right, so that was fairly straightforward. It's more a question than sort of a statement. We think that was a nice, easy way to follow it through. Okay, that's taken about an hour, which is about what I thought it would. And that's sort of as much as I've planned for today, except for to go, do we have questions? All right, I'm going to leave that there for a second. So if we don't got questions, then I can finish early and we can all go home and have some lunch. If you've got questions about pretty much anything else from the Maths for IT course, what we might do is we can sort of you can go through and ask those now if you want. But because this was the only thing people actually said they were having difficulties with, this is all I've sort of prepared for ahead of time. That's the other thing to say with our revision seminars. Email us if you've got something you want us to do for a revision seminar. Go, hey, I'm having trouble with this, or don't understand this topic. All right. So with almost any of these things, it's just a matter of going, what are the key definitions? You'll see that there were very few definitions at the start of this, but we've put them out there so that we can use them to solve our problems. All right, well, thanks for your attention. I'm going to stop this recording, and if we've got more questions, I'll create a new one. Okay, thanks.